So what's up guys, this is me again, the Round Bottom Flask, and welcome to the part 1 of our video lecture series for Colligative Properties of Solutions. So for this video, I will be giving a brief introduction on what are the colligative properties of solutions, the concept of vapor pressure and boiling point, and I will also discuss one colligative property, which is the Raoults Law. So when we say colligative properties, they do not actually depend on the identity of the solute of the solution, but rather on the amount of the solute in the solution. So what does that mean? Let's say we have two solutions. One contains 1 molar of glucose, while the other solution contains 1 molar of, say, table sugar. Now, these two solutions contain different solutes, okay? However, they exhibit the same concentration of solute, thus they will exhibit the same colligative properties or the same magnitude of colligative properties. So what are these colligative properties? So these are your vapor pressure, your boiling point, your freezing point, and your osmotic pressure. So let's go back to those two solutions that I have talked about. So let's say si glucose solution kag si table sugar solution, pareha sila 1 molar, diba? So although lainay ang identity ng solute nga ara sa ila, they will have the same vapor pressure, they will have the same boiling point, the same freezing point, and the same osmotic pressure. So what do we mean when we say vapor pressure and boiling point? So let's have this illustration here. So diba, in the first picture here, or in the picture on the left part of the picture, so we know that at room temperature, some of the liquid escape through the gas phase. So that is why nga kung ang baso ibutang nga wala taklob, eventually maubos, or rather, let's say may ara ta tubig nga ara sa sulod ng baso, kag we leave it there without covering the glass, eventually the liquid will disappear, eventually the contents of the glass will disappear. So ano to na tong natabo sa tubig nga sa sulod ng baso? All of the water has actually evaporated or has been converted in a gas phase. Now, if the lid of the container is covered, as we can see in the flask on the left here, some of the liquid will evaporate, right? Will escape to the gas phase. Now, if that container is closed, so the gas molecules will accumulate, or the vapor will accumulate here at the surface above the liquid, and a time will come that the space above the liquid will be saturated with will contain enough vapor. So what will happen here? Some of the vapor will go back to the bulk liquid. Okay, so what happens here? So while some of the molecules in the liquid phase will escape to the gas phase, some molecules in the gas phase will revert back to the liquid phase. So that this action is actually dynamic. Okay, so that means dungan evaporate ang liquid, at the same time dungan man condense ang vapor pabalik sa liquid. They both happen at the same rate. Now, the vapor here above the liquid, since they are already in the gas phase, will exert some sort of pressure. And that pressure is what we call as the vapor pressure. Now, the liquid will boil when the vapor pressure of the liquid is high enough that it is equal to the atmospheric pressure. So what happens here when the liquid boils? So that boiling action that we see is due to the bubble, due to the liquid escaping to the vapor phase at the middle of the bulk of the liquid. If you can see here in our previous diagram, the the ones that breaks into the gas phase are the liquid in on the surface. Okay, the liquid molecules on the surface. So why is that so? It is because that the liquid molecules at the surface is the one that feels the weakest intermolecular forces. Because here, kung ari di siya sa bulks ng liquid, it feels intermolecular forces at all directions, while the liquid molecules or the liquid particles on the surface only feels intermolecular forces below it. Okay, so wala intermolecular force nga ara sa babaw nila. Okay? So ang kakatabo is sila ang mas hapos mag-break away to the gas phase kay ang intermolecular forces lang nga nagapugong sa ila is ari sa gahold sila sa liquid phase is ari sa dalom kag ara sa kilid. So going back here, so when the water boils, even the liquid has become hot enough that even at the middle of the bulk liquid, evaporation occurs. So, amo na nga may kita nga bubbling during at the boiling point. So, what is the Raoult's law? Now, Raoult's law states that the vapor pressure of the solvent containing a non-volatile solute or solutes is lower than its pure form. So what happens here is actually the solute in the solution actually lowers the vapor pressure of the solvent. Okay, so that means that the vapor pressure here of the solution will be lower than the vapor pressure of the pure solvent. So we have this equation here wherein X subsolvent is the mole fraction of your solvent in the solution. Now this equation, it only holds true when your solute is a non-electrolyte. All of the other components in your solution aside from the solvent are non-electrolytes. Now, if we only have one non-electrolyte solute in the solution, the Raoult's law can be expressed using the mole fraction of the solute. So we know that since we only have two components, that means that the mole fraction of the solute plus the mole fraction of the solvent is equal to 1. Remember that the sum of the mole fraction of all of the components in the solution will always be equal to 1. Kung hindi siya equal to 1, that means may sala sa calculation niyo sa mole fraction. Okay? So, we can express the mole fraction of the solvent in terms of the mole fraction of solute by transferring this to the other side of the equation. So, from positive, maging negative siya. So, the mole fraction of the solvent is equal to 1 minus the mole fraction of the solute. So, going back to our expression of the Raoult's law, we substitute this expression with this expression here, and we'll be given this expression here. Now, we distribute the vapor pressure of the pure solvent into these two these two variables here enclosed in the parentheses. So ang final or ang working equation mo, if we get the vapor pressure of the solution in terms of mole fraction of the solute, will be this one. Okay, so either will do. We can use this one, we can use this one, whichever makes you feel comfortable. So how does the solute lower the vapor pressure of the solution or the solvent? So what happens here is that is that since your your non-volatile solute particle will be dissolved in the solution, what happens here is that in order for the solute particles to be dissolved in the solvent, it should form a stronger non-covalent interaction with the solvent particles enough that it will break the non-covalent interactions between the solvent particles. So what happens here is that since mas kusog ang non-covalent interactions between the solute and the solvent, kag between the solvent particles, so what will happen here is mas attracted si solvent particles kaysa sa solute particles. So since mas attracted na siya sa solute particles, it would like to stay there in the liquid phase where there are solute particles present. Okay? So what will happen is it will be harder for it to go into the gas phase. So what happens here is that at equilibrium, mas gajutay na ang gas molecules or ang vapor molecules mo kaysa nga sa molecules mo nga ara sa liquid phase. Kay tungod nga ang imo nga liquid molecules mas gusto niya magstay sa liquid phase nga ara ang imo nga non-volatile solute nga mas kusog ang iya nga non-covalent interactions with it. So the presence of this non-volatile solute makes it harder for the solvent particles to escape from the bulk liquid into the vapor phase. I hope you get what I'm saying. Now, what happens if we have a volatile solute? So, what do you mean when we say the solute is volatile? That means that the solute will have its own vapor pressure. So what happens here is that both components, both the solute and the solvent, will affect the vapor pressure of each other. So we can also apply Raoult's law on the vapor pressure of each component of the solvent of each component in solution. Thus, the vapor pressure of the solution is the sum of the vapor pressures of the two components. Okay, so applying Raoult's law here, so ang component 1 will have its own vapor pressure in solution in accordance with Raoult's law. The component 2 will also have its own vapor pressure in accordance to Raoult's law. So ang vapor pressure sang solution mo is ang sum sang duha ni ka vapor pressure sang imo nga component. So substitute ang ini nga expression with this one nga na-derived from Raoult's law. So this will be your working expression in a working equation in determining the vapor pressure of your solution if all of your components in your solution are volatile, or if 2 or more components in your solution are volatile. So I will show you an example here. So let's have this sample problem here. Consider a solution formed by adding 10 grams of glucose to 1 liter of water. Calculate the vapor pressure for this solution at 20 degrees centigrade. The vapor pressure of pure water at this temperature is 17.5 torr. Now, every time we answer problem-solving questions like this one, wherein a solution is required, or a process on how did you arrive your answer is required, importante gid that we first indicate our given. So, ang given is dira mo ilista tanan-tanan nga information that you think will help you solve the problem to arrive at the correct answer. So, in this case, we have 10 grams of your glucose, which we will abbreviate in this case as GLU, plus 1 liter of water. So because we added 10 10 grams of glucose to 1 liter of water. Then we know that the vapor pressure of pure water is indicated here, which is 17.5 torr. So also we indicate what is required. So what is required is the vapor pressure of the solution. So isulat mo man kung ano ang required. So then we go to our solution. So we know that this is a classic example of our Raoults law. So to make things, or to help you remember, I think ibutan ko na lang una ang formula nga gamiton for Raoults law. So the vapor pressure of the solution, which is equal to the mole fraction of our solvent, which is water, multiplied by the vapor pressure of pure water. Then we know that the mole fraction of water is equal to ang number of moles ng water nga ara sa solution kag ang total number of moles. Since ang components ng sa imong solution is si glucose kag si water, so it will just be the number of moles of your glucose plus the number of moles of your water. So we know what we should solve first. We should solve first the number of moles of each component. So number of moles of your water. So how do we get that? We get that from our volume of water. So we know that we have 1 liter of our water. So what we do first is we convert this to milliliters. So we know that 1 liter is equal to 1,000 milliliters. So that will be our conversion factor. So after mo convert siya sa milliliters, paano mo siya i-convert sa number of moles? So we know in order to convert it to moles, we have to convert it first to grams, because if you remember your stoichiometry, the direct conversion is usually from moles to grams using the molar mass of a compound or an element. So paano tani siya ma-convert sa grams? We use the density of water. And we know that the density of your water, so I'll just write it here as a given. We know that the density of your water is 1 gram per milliliter, right? So we can use this as our conversion factor to convert our volume in milliliters to its mass in grams. So we have 1 gram of your water over 1 milliliter of your water. So ma-cancel out na sila. So ang bilinsi mo is ang gram. Oops. Erase ko lang yung parentheses. Okay? Karon, ang kinahanglan mo is ang number of moles. So, we know that in order to convert grams to mole, we need the molar mass of your water. Now, I will leave to you on how to calculate the molar mass. So, what I got after calculating the molar mass of water is the molar mass of water is 18.016 grams per mole. So, that will be, we will use that as our conversion factor. So since ang ginapangita is ang mole, sala ni siya, moles ng water is 1 mole of your water. So ari siya dapat sa numerator sa atong conversion factor over 18.016 grams of your water. So what you'll get is around, sorry, may na-ready na ako nga solution set. So is around 55.50, that is 0 rather, 55.50622 mole of your water. Now, why do I put so much decimal places? Because, or why do I put so much decimal values? This is because this is not yet our final answer. So we will still have to use this in our equation here, in our in our mole fraction, and eventually pagkuha ta sang aton nga vapor pressure sang solution. So I write as many decimal places as necessary in order to reduce or to mitigate the errors due to calculations from rounding off. Okay. Now, since we got the number of moles of your water, we will also solve for the number of moles of your glucose. So we know that, I hope it's still visible. Yep, it's good, it's still visible. So the number of moles of glucose is equal to, we have 10 grams of your glucose. So we also use the molar mass of your glucose. So in this case, the molar mass of your glucose is 180.186, if, correct me if I'm wrong, 156 kile, sorry, 156 grams per mole of your. So that, oops, hindi siya makancel out. So this will cancel out, and your final answer is equal to 0.055507 mole of your glucose. So we already got that. Then we can now solve for the molar mass, or rather the mole fraction of your water. So we substitute these values to our equation here, which is equal to, so 55.50622 plus 0.055507. So sa numerator is ang number of moles of water. So that is 55.50622. Which is equal to 0.999 tatlo na di siya ka 0 and some other value. So I just rounded it off to the nearest non-zero digit, which is 0.0999. Okay, remember that mole fraction does not have a unit. So we can now solve for the vapor pressure of the solution, which is equal to 0.999 multiplied by 17.5 torr, which is equal to, rounded off to four significant figures, 17.48 torr. So this is the vapor pressure of the glucose solution in this problem. So let's have another example here, wherein both components now have are volatile, rather. So we have a solution containing 50 grams of heptane and 50 grams of octane with their respective chemical formulas. The vapor pressure of pure heptane and pure octane at 25 degrees centigrade are 45.8 torr and 10.9 torr respectively. Calculate the vapor pressure of the solution at this temperature. So again, masulat kita sa aton nga given. So aton nga given is we have a solution containing 50.0 grams of your N-heptane, which is mixed with an equal mass of your octane. So we are also given the vapor pressure of your heptane, which is equals to 45.8 torr, while the vapor pressure of your octane is this one here. So after that, we indicate what is required in the problem. So I'll make my handwriting a bit smaller because yeah, medyo gutok siya. Is the vapor pressure of the solution. So how do we solve this one? So remember that we already have we have two volatile we have a solution that it is formed by mixing two volatile components. Therefore, the Raoults Law for a solution containing a non-electrolyte solute will no longer be applicable, as we have seen, unlike the first problem that I have shown earlier. So thus, the vapor pressure of the solution will be equal to the vapor pressure of the two components. Let's say our component 1 is our heptane, and our component 2 is our octane. Okay? So what we need to do is we get the vapor pressure of each component in the solution. So may ari kita muna. So this is where we use our Raoults Law. So in order to get the molar rate, the mole fraction of each component, we need to know the number of moles of each component in the solution. So we know that the mole fraction of heptane is equal to the number of moles of heptane divided by the total number of moles, which is just the sum of the number of moles of heptane and octane, since there's only two of them in the solution. So same goes with the mole fraction of your octane. I hope you guys follow. So I'll just move this a bit upward here, since we already have the given and the required. So we solve for the number of moles of our heptane. So we know. So we use the molar mass of heptane and the number of grams of heptane to get the number of moles of heptane. So the same that we did in our first problem, we convert the grams of heptane to moles using its molar mass. So the molar mass of heptane is, let me check my pre-solve. Okay, I've already solved this beforehand, is 100.198. So we have 1 mole of your heptane over the molar mass, which in grams, which is, or in grams per mole, which is 100.198 grams heptane. So amo ni ang aton nga kumbaga nga conversion factor, ang aton molar mass. So that is equal to, cancel out si ang grams heptane. I will write again the all decimal places, or as many decimal places as possible. So this is 0.4990196 mole So the mole octane, we also do the same thing, but we now use the molar mass of octane, obviously, as our conversion factor. Is equal to sorry if it seems congested. Oops. Equal to 0.22. So the molar mass of your octane is 114.224 grams per mole. Or rather, the molar mass of your octane, rather. Sorry guys if it looks congested because, yeah, base hindi siya kitaon. Oops, I accidentally canceled out the number of the mole octane. So that is equal to 0.43773638 mole octane. Yep. It's good that it's visible. So then we now have the number of moles of each component. We can now solve for their respective mole fractions. So this is equal to, so substitute lang ang values sa atong equation here for our mole fraction. So that is equal to, again, mabutang man ko as many decimal places as possible. So this is around 0. For n-heptane, the mole fraction is 0.53277. I hope you follow. So for the mole fraction of octane, so we have the number of moles of octane, which is this one, which is the 0.43 something. 73638 divided by 0.4990196 plus 0.4377368, and that is equal to 0.467293. So that is the mole fraction of each component. Now we have the mole fraction of each component. We can now get the respective vapor pressure in the solution, which is equal to, so P1, so the P1 null is the vapor pressure of your pure heptane. That is equals to 0.532707. Or if you want, pwede ka mo kadiritso na lang amune. So, sorry, I forgot. So, pwede man, since we have this expression here and this expression, we can actually substitute this one to here. Okay, so that will make, we have already seen that earlier, so that means the vapor pressure of the solution is equal to x1 P1 null plus x2 P2 null. Okay, thus, substituting the equation, so substituting these the values that we've obtained and also on as indicated on our given, so x1 is 0.46 0.532707 multiplied by our mole fraction on heptane, which is 45.8 SOR, plus the mole fraction of your octane, 467,293, multiplied by its respective vapor pressure in pure form, which is equal to 10.9 SOR. So solving this in your calculator, we can put this in one go. You can input this in your calculation in just one line, and it will give you the answer, which is rounded off to 4 significant figures, is equal to 29.49 SOR. So this is the vapor pressure of the solution. So that's the end of our video. That's the end of our video. If you find this video interesting, please like this video and don't forget to subscribe to my YouTube channel for more videos on chemistry. So again, this is the Round Bottom Flask signing out. See you guys